This is a video for Edexcel Further Pure 1. Coordinate Systems 2, the Ellipse and Hyperbola, Section 2.4, Focus Directrix Properties of Ellipses. In the last video we met the idea of eccentricity, which is the distance of a point on the conic section from its focus, PS, divided by the distance to the directrix, PM. And that for different values of E, we had the three conic sections, ellipse, parabola and hyperbola. So we're going to concentrate on the first one of these, where E is between 0 and 1. That gives us an ellipse. Here's the essential information about a standard ellipse. We have its Cartesian equation, which we've met before, the idea that the eccentricity is between 0 and 1, and now we have information about the foci and the directrices. The foci are at plus or minus AE0, so they're lying along the x-axis if A is greater than B, and the directrices are x is equal to plus or minus A over E. If we had B is greater than A, then we would have an ellipse in this sort of fashion with the major axis along the y-axis, and so the foci would be on the y-axis and the directrices would be y equal to, so parallel to the x-axis. This information is given to you in your formula sheet, so you don't need to worry about learning it. However, from it we can develop one interesting and important equation, which is that b squared is equal to a squared 1 minus e squared. It's quite a straightforward, although lengthy, proof to do this. However, it simply involves using Pythagoras' theorem to work out the length of PS, or PS squared, and then equating that to E multiplied by PM squared. Well, Pythagoras' theorem for PS squared gives us this distance here, which is x minus AE, all squared, plus the height y squared. And PM will be from the directrix, which is A over E, back to x, so PM squared will be equal to A over E minus x all squared. And if I take out E as a factor from that, it will be 1 over E squared multiplied by, and then in the bracket, A minus EX all squared. Now on the next slide, I'm just going to equate PS squared to PM squared. So there we are, PS squared is equal to EPM squared, gives this equation. And then it is, as I say, a lengthy but quite straightforward process to multiply out these brackets and gather together terms in x squared and a squared. And then we can see we get to this line here. Divide through by 1 minus e squared, and we end up with y squared over a squared 1 minus e squared. But in the standard equation, of course, that is equal to b squared, so that b squared is equal to a squared 1 minus e squared. Pause the video, take a little bit of time to look through that and make sure you could reproduce it should you be asked to. Well, I'm now going to use some of this information in a typical A-level question, which is this one here. We've got an ellipse which has equation 4x squared plus 9y squared equal to 36. We're asked to find the eccentricity and to sketch the graph showing the directrices and the foci. Once we've done that, we're asked then to show that PS plus PS dash, that's the focal distances added together, is equal to 6. Well, the first part of the question we're going to first of all change this into its standard form to give us the values of a and b, and once we've got that, that will allow us to use that new expression that we had, b squared is equal to a squared 1 minus e squared, to work out the eccentricity. And once we've got this eccentricity and the values of a and b, it's very easy then to work out the coordinates of the foci and the equation of the directrices. So let's do that in a little bit more detail. So here we have the expression that we were given. Dividing through by 36 gives us x squared over 9 plus y squared over 4 equal to 1. So immediately we can see that a is equal to 3, b is equal to 2, and we have that b squared, which is 4, is equal to a squared 9 and 1 minus e squared. So dividing by 9, subtracting from 1, that gives us that e squared is equal to 1 minus 4 over 9, so that's 5 over 9, and therefore the eccentricity e is equal to the square root of that, root 5 over 3. The foci are at AE, so that we have multiplying by 3 gives us that the foci are at S is root 5, 0, and S dashed at negative root 5, 0. So this is at negative root 5 and this one root 5. The directrices, x is equal to negative a over e and plus, so plus or minus a over e, and that gives us 3 plus or minus 3, and then multiplied by 3 over 5, so they're at, sorry, beg your pardon, 3 over root 5, so they're at 9 over root 5, plus or minus. So minus 9 over root 5 and plus 9 over root 5. So there we are, there's our sketch with all the information put on it. Remember again that you don't need to commit this to memory. It is something which is given on the formula sheet. The next part of the question asks us to show that the focal distances added together, so that's PS plus PS dashed, is equal to 6. Now we could try and work out each of PS and PS dash using Pythagoras' theorem maybe, and then show that they sum to 6. However, there's a little bit of a trick, which instead of using PS and PS dash, we use the distances to the directrices, so PM and PM dashed, because we know that PS is equal to EPM, and likewise for PS dash, that's EPM dashed. So therefore PS plus PS dash must be equal to E multiplied by PM plus PM dashed. But that's a rather easier thing to work out, because we know that the directrices are at plus or minus 9 over root 5, so we just need to double that. This is 2 multiplied by 9 over root 5, and therefore this must be equal to root 5 over 3, which is E, multiplied by 2 times 9 over root 5. Cancelling out the root 5s, dividing by 3 gives us that is equal to 6. So a little bit of a trick there, using the property that PS, the focal distance, is E times the distance to the directrix. And here it is written out neatly for you. Now this property is actually true of all ellipses. The fact that the focal distances added together is a constant. And in fact 6 here is equal to 2a. So we can say in general that PS plus PS dashed is equal to 2 multiplied by a. It is one way that you can actually draw an ellipse. If you take a piece of string and fix with 2 pins, then your piece of string is loose, but if you stretch it out with a pencil here, then moving the pencil around, keeping the string taut, will produce an ellipse. So the focal distances of an ellipse, the sum of, is equal to a constant equal to 2a. Well, finally then, just to show you the formula sheet that you're given, this is all the information in your formula sheet, so you don't need to learn it. So we have the standard form, it's Cartesian equation, the parametric form, the fact that the eccentricity is less than 1, and that gives you that b squared is equal to a squared 1 minus e squared, and with the information of a, e, and we can calculate the foci and the directrices. That concludes this video about ellipses. In the next one, we're looking at the focus directrix properties of hyperbole.